Hello fellow skeptics, I'm Luther Name, and this is the 14th video in the series on the broad topic of is something wrong with modern physics, and if so, what, and can it be fixed? Now I've been dwelling on the Doppler and aberration elements of special relativity because I think that that's all there is. I think the kinematics are a misinterpretation of how we're measuring and interpreting the acceleration of objects when to various high velocities when we're using electromagnetic radiation to basically initiate all the kinematics that we're measuring. And we've gotten it wrong because we haven't fully understood the Doppler. Now, in the last one I began to investigate, in the last video, I'd begun to investigate the aberration, an aspect of Einstein's development in his 1905 paper that interlinked both the Doppler and an aberration effect. The aberration has been essentially unexploited and unexplored. And part of that's because of the Minkowski reformulation, which focused on the kinematics. The problem with the kinematic part, as Einstein and other people have looked at it, is that when you do the kinematics using the Lorentz transforms, when you include the Lorentz transforms come from a very legitimate aspect of the propagation of electromagnetic radiation. And it has to do with the Doppler and, as Einstein showed, with an unknown feature called the aberration. The interpretations of what was happening in both the acceleration and measurement processes were just a misinterpretation of what was happening with respect to kinematics. And the inclusion of the Lorentz transforms in terms of describing the propagation of physical matter to me it's not legitimate. It doesn't fit any investigation that you do. You can't do it. You cannot apply the Lorentz transforms to kinematic propagation. It doesn't come from that, and it doesn't apply to that. So we have an issue with respect to the Doppler and the aberration in that we've convolved electromagnetic phenomena associated with the radiation pressure, which I have described in a prior video, and an unknown aspect of that, which is also affects the kinematics of objects, which is the aberration. Now here I'm going to continue and complete my initial discussion of the aberration with another scenario. I think the scenarios make it a lot easier to see what's happening. But what I'll do in the next video after this one is I'll treat yet another scenario which ties both the radiation pressure and the aberration effect together in a way that I think will produce a surprising result. Again, I think this is academic at this point. There may be technological issues that are already unknowingly being affected by the lack of knowledge of how the Doppler and aberration work together, and in this particular instance in terms of how our detections, our sensor systems are operating. And I think that there is some physics that we've missed and some interpretations that we're not getting correctly. And whether those they will have academic impact, but whether they have any practical or technological impact, I think they may. But we'll have to see. We'll have to wait to quantify that. So in the meantime, what I've done is I've again prepared some visual materials to describe what's going on with the aberration effect. And it's all leading up to a final scenario in the next video that, as I said, may surprise many people by the ramifications. So with that, let's go ahead and get to the visual materials. What we're going to do is revisit the scenario that we just showed, which is radiation coming in on a flat surface, moving across the flux at some angle. What we're going to do is redefine the angles that we use because we're going to establish another scenario for measurements so that we can have a way of quantifying what exactly is happening. And in fact, this scenario that I'll be describing, in fact, represents a series of measurements that have been taken that have produced unexplained results. And when we get finished with this discussion, we will have a much better handle on perhaps what is going on and maybe exactly why the unexpected results occurred as they did. In this particular instance, this is just a review of what happens. The radiation coming in from the sun on an object moving transverse through the radiation from the sun. That radiation, when it's reflected off of this object, experiences a deviation. If there were no motion, or in using just the static model for radiation pressure, what we'd have is the incident angle and reflecting angle are the same. What happens is because of the transverse motion, has a component of motion here along perpendicular to the flux direction, we wind up with a deviation of the radiation. If there were no deviation and this was symmetrical, there would be no net recoil. Radiation pressure on the object in terms of the incident angle and the output angle, reflected angle, would leave a zero net momentum change, and therefore there'd be no motion attributable to this reflection. However, when the object is moving, you have a deviation of the ray and there's an asymmetry then, and so there winds up being a net recoil on the object in this direction as it is deviated in the forward direction and the direction of motion. So what we have to do is redefine the angles that we're using. This is the way the aberration was defined by Einstein using the angle phi prime and phi, and which are the angles associated with the incident flux of radiation. However, when we make a measurement, we are looking back at the source of the radiation itself. And so in the second scenario where we're actually measuring the Doppler shift associated with the incoming radiation, well, then what we have to do is have an angle in there that modifies this to represent what that angle is. And what we do is when we look at the relationship of the various angles as Einstein used them to define the aberration versus the angles we use when we're actually looking at the sun. And what we're doing is looking at the apparent aberrated incident radiation. We're looking back at it, and so we're looking at a cos theta prime. We have phi plus theta equals pi, supplemental angles. We have phi prime plus theta prime equals supplemental angle. And so what we have is this particular relationship, and with respect to the normal idea of incident angles and reflected angles, we have this relationship in the angle psi that we've identified here. But this now becomes the new aberration angle equation that we're looking at in terms of the transverse beta and the actual angles associated with transforming phi prime into theta prime, which is where we're looking. When we do that, this is the equations we'll be working with. We have the standard Doppler expression. Notice it's given in terms of cos and phi. We're not looking at that. We're looking at phi, but we're also looking at an aberrated phi. So what we need to do then is to identify what the Doppler expression is when we're looking back at an angle theta prime. And when we make the modifications here, as shown on the slide, and these slides are only shown so that somebody who's who's inclined to can go back and see what the process was in making these transformations. They're all standard trigonometric transformations. But the key is you've got to be measuring something, and to be measuring something, you got to be looking at it. And what we wind up with is this is the Doppler expression we're going to be working with, not the one up here, but this one. This is the correct one. And these are angles we can measure directly. So again, what we're going to be looking at is the sun on the Earth, and we're looking from the Earth towards the sun. And so the nominal angle from the Earth orbit to the sun is 90 degrees. So we have phi equal to 90 degrees, and phi prime is close to being 90 degrees. So that we're dealing with angles where the cosine is very small. And so this is what we're doing, is measuring this particular Doppler expression. Again, we're using a small beta approximation because the speed of the Earth around the sun is 30 kilometers per second, and that leads to a beta of 10 to the minus fourth. Now, if we look at this, we have an angle that we can identify in which there is no Doppler expression. And that occurs when cosine theta prime is minus beta over 2. It becomes an angle. This is called a zero crossing angle Doppler. And it's offset from the center of the sun by an angle given by beta over 2. In other words, we're not looking at the center of the sun. We're looking offset by an aberration. And that aberration is offset from the center line from the telescope on Earth to the center of the sun, as that offset angle is minus beta over 2. Now, interestingly, what we'll show is that, and we'll show this in the next view graph, in any direction you go, no matter how you change theta prime, as you scan it across the sun, nu prime will always be less than nu. And when nu prime is smaller, that means that the wavelength is longer. And when wavelength gets longer, if you look in the visual part of the spectrum, longer wavelengths go from blue towards red. So we call these redshifted. No matter how you look at the measurement process here, all nu prime relative to this center position will always be redshifted. That gives rise to an issue that has perplexed spectroscopists, academic physicists for over 100 years. They've measured it, they've seen these effects, but they don't know why it happens. Why is that? Because they have ignored the aberration as a significant component associated with measuring the Doppler. So it's not just the radiation pressure that's been an issue, it's also that particular instance. Now, what's the value of it? Well, it's an academic exercise in making these particular measurements. What's deleterious is that in order to try and explain what's going on, they invoke other physics that just have nothing to do with it. They're grasping at straws because they don't have an answer. And like when we look at various aspects of Newtonian gravity, when there are difficulties justifying certain measurements and they don't seem to fit, we don't go back and say, well, maybe we've missed something. They just never make that self or introspective statement. Maybe we've missed something. They don't say that. So here's what we normally get. If this is the Earth moving in this direction, what we have here is a line of a telescope looking directly at the center of the sun. This is on the equator, and as we scan from one limb of the sun, and this is called the limb of the sun, either the left or the right, across the center, what happens is we measure a Doppler, and that Doppler actually goes to 0 at this offset angle of minus beta over 2. And as we continue to scan and take Doppler measurements along that equator, the Doppler expression, Doppler decreases. Nu prime is less than nu, redshifted. And it worked in either direction. It's always the case when you make these measurements. That will always be the case. You will always get a redshift on these measurements. Nobody's known where they've come from. Now we have at least a tool to begin to investigate where that particular anomalous result. This was measurements that were made on an ionized line of iron in the sun. And so it was called uh, the iron line redshift. It's a strong line, it was easy to measure, and they got these anomalous redshifts as they scanned across the sun and didn't know where they came from. So now we have a means of addressing that problem. So with this particular description of the aberration in terms of the frequency, how it affects how we measure the frequency, things I haven't gotten into that I think may impact this is calibrations. When we look at something like a spectrum on the sun, which is what the scenario that I just described was really considering. The issue is we're really comparing what we're measuring when we're looking at the sun with things that we see in the laboratory and that we've measured in the laboratory, and so we think we've calibrated things. I'm not so sure that we have. I'm not so sure that our calibrations are consistent. And sometimes our calibrations are done in such a way that from an empirical perspective they hide things that otherwise would be exposed. We're very good with technology. We're very good with coming up with ways of measuring things. But I'm not sure that what we're getting is all the information that we need or interpreting what we're measuring correctly. So with that, what I'm going to do is defer any further discussion to, as I've alluded before, to the next video, which will describe a series of interrelated final scenarios having to do with telescopes and how they actually work. We really don't know how they work. We think we do, but as the discussions with the Doppler and Aberration have gone, there are things happening that if you don't understand a lot of details about how your apparatus is configured and how the environment that you're in impacts what you're measuring, you're not going to know what you measured. And in fact, what I'll show is in some instances you may be not able to measure certain things. If you're not careful, your apparatus will simply not see certain things that you think it should be seeing. And if you don't see something, if you can't measure it, well, then you don't know it exists. So we'll talk about that in the next one. I'm Luther Name, and stay skeptical. Leave a comment. Appreciate your comments, and talk to you in the next video.